But now I'd like to introduce Dr. Bjoern Peters to give the analysis resource overview talk. Thanks very much, Bjoern.
Thank you, Nina. Thank you, Alex, for kicking us off. So as Nina was saying, I'm going to talk about the companion side of the IEDB database that Alex talked about, namely the analysis resource. And there's really two bits here, the traditional tools.iedb.org, what we sometimes now call the legacy side, and the next generation tools side. And basically, what I want to point out here is that these two sites are essentially going to be a migration of everything that we have currently on the legacy side on the left, which is currently more complete, is going to be migrated into the next generation tool side, where the same tools will be implemented in a way that improves usability, improves function of these tools, makes them more consistent as the traditional side has grown over time. Overall, I want to point out also that this talk, like Alex's, is really meant as a summary to get you an introduction of the overall capabilities of the tools that we have in the IEDB. There's going to be a lot more detail on everything. So if you're thinking things are going too fast, there's going to be a whole day tomorrow where we'll talk about the tools in detail. So starting talking about the next generation side on the right here, this is launched in 2023. So let me just hide my Zoom controls here, they're in the way. Okay, it's better. So it's a multi-year process where we've been kicking off essentially building the backend of the site and have started to migrate individual tools over with the goal to simplify the user experience. As I mentioned, I mean, ultimately the tools have been created in 2004 and from then have been grown kind of organically over time, and we have done some attempts to keep them to make them somewhat consistent, but they're not. And so in this redesign, we are trying to make sure that the user switching from, say, class 1 to class 2 tools and more new tools can use the same skills to do them throughout. We also want to increase the existing functionality. In some cases, there were options that are not available in the old implementation. We want to add new functionality as we go along. I mentioned the consistency before, and also the layout and aesthetics. People have been telling us that our tools are not the prettiest, and we don't like to hear that, so we want to address that. The first release that was done focused on T-cell epitope prediction class 1 tools, and that's kind of what you see up here, the cluster analysis and pep match. And there was a second release that came out. There was multiple ones in the backend, but these are the first public releases. The second one focused on cancer applications, mutated peptide generation, variant comparison, and PEPX. And essentially, when you look at the overall, so what I should say again, that's like on day 2, Jay is going to present a broader overview and go into more details for all of these things here. Versus these are the releases that we've gone through. I mentioned the first releases focusing on the essentially T-cell class 1 prediction tools. Then the release 2 that I mentioned in the last slide really deals with the cancer-specific tools that are belonging to the CEDAR component of the IEDB, and Zeynep is going to talk about those on day 3 in a lot more detail again. So then we have other releases planned. Class 2 should be coming up. That's in the later stages of testing at this point. And then we're going to go for B-cell predictions coming online sometime beyond Q1 of 2025. So this is a little bit more how the page looks like. This is what you see now on the home page. And one of the things that we wanted to have is the ability that you just can directly run what's on the home page. We have seen that people otherwise, when you look at an empty screen with an empty form, you might be wondering, like, what do I do here? And then they just stop. So here you can just run it, and then obviously by learning by doing, then you can see what happens and adjust from it. Once you have run the predictions from the home page, you can also just go directly here. This is, again, the page that's going to be explained in much more detail here. And I realized because of the size here, it looks overwhelming. But essentially, it goes through collecting the input sequences. You have the input parameters in an easy-to-update format. your prediction method selection, and you get your output results table, which is now sortable, filterable, and all these things. And the cool and most important new feature that comes with the next generation tools is this ability to take the results from one tool and pipe them into the next, so that you can, let's say, predict binders from a given protein sequence, choose the alleles that they are for, cut off and say only the ones that are predicted above a certain score should be filtered on, and then cluster those and see where they fall in the protein sequence. The other thing that we've been spending a significant amount of time on is the documentation, which that was probably in one of the worst shapes because it was spread throughout. And by having consistency in the user interface, both in entering the tool parameters and in how the reporting looks like, we are hoping to provide better quality help that is actually applicable across all the tools that we have. So this is the next generation tools. And again, the tools there are the same pretty much, or essentially the same as in the original legacy site, which I'll talk about now. That is, as I mentioned, like a large collection of tools that has grown from 2004 over and over in terms of new versions of tools, but also new types of tools that have been added. And this is kind of the main subdivision into T-cell and B-cell epitope prediction tools versus analysis tools. Again, day 2 will go into much more detail. And the prediction tools is really, I think, what this this is one of the 2 buckets essentially of tools that we have, which are based on machine learning, taking advantage of the data that we have in the IEDB. So where we take data that is such as MHC binding data or 3D crystal structures of, say, antibody antigen complexes or T-cell assay data, and then run prediction models that take these inputs and their known outcomes and try to find patterns to extrapolate to new examples. So from the training data, you're building prediction models, and then you have your input data that you can now use in your tool, run through the model and get your prediction results. Here, all as MHC binding is always an easy example, but the principle applies really to all the tools, prediction tools that we have on the site. So how do you get to the current analysis resource page? If you go to iedb.org, you have on the right-hand side direct links to some of the most frequently used tools, but you also can click here on this menu and kind of get the same kind of links, or you can go directly to tools.iedb.org and get there. This is the classic homepage where all the prediction tools, well, the tools, T-cell tools, B-cell tools, analysis tools are accessible in different tabs, or also linked here from the main page. Then there's different things that I'll talk about briefly, the API that we have and the standalone tools, and the data sets that we have available that we're used to train the tools or could be used to test the tools. And then, as with everywhere else on the site, we have links to the help system. Alex showed that in the last talk just briefly. And you can also email us directly at help@iedb.org. So on the T-cell epitope prediction link, when you click there, you're getting essentially a list of all the different tools that are currently available. And these are, say, the MHC binding predictions. And looking at the first one here, predicting binding to MHC class 1 molecules. This is the kind of front end of these tools, where you start by entering a sequence, and then you're supposed to pick a prediction method. And here's one of the things that I want to point out. We have these different methods that were generated over time. And what we always have at the top is a recommended prediction method. And in this case, we have a recommended epitope predictor versus a recommended binding predictor. So the binding predictor really predicts IC50 nanomolar affinities, versus the epitope predictor actually predicts a likelihood of being naturally processed and presented by a given MHC allele from a cell. And so that is more important that performs better in predicting actual epitopes. So now if you're wondering where do these things come from, we are performing a large amount of benchmarking efforts. This is the one that actually made us switch to the net MHC pan ligand elution as the recommended method. So we're running these examples, comparing the performance of different tools, and based on that, then deciding what is going to be recommended. And we're being conservative with that. We don't want to switch back and forth So essentially, once a method has been consistently predicting better than others, that's when we make the switch. And that's obviously also why we give others who have different opinions. You can still use all the other tools. But if you're saying, well, I just want to use what you guys think is best, then go with the recommended version here. So this is actually showing in an AUC plot the prediction of vaccinia virus. This is the vaccine for smallpox derived epitopes in a mouse study. The mouse study has the big advantage that this could actually be done systematically over and over, because these are inbred mice. You can get the same results over and over again and really systematically test everything. I thought it was a great study done by David Sharkey, Australia. And the performance is really amazing. When you see here, you have an AUC of 0.977, that is the area under this curve. And essentially, you have this true positive rate going up, where you essentially get 90% of the epitopes are recovered in the top 0.05%, I believe. Sorry, 0.5%. So this then led to this recommendation, but this is not the only benchmark we're doing. The other one is that we're doing is that we're taking the data that comes into the IEDB on a weekly basis and run all the tools that we have implemented in the IEDB on those data sets and perform calculate AUC values as well. Now, at the same time, when we originally did this, we just used the AUC values. We said, awesome, we can just average them. But the problem is that different data sets are intrinsically differently hard to predict. If you're doing overlapping peptide scans, say, of a protein, and you're looking for trying to predict which one is a binder or not, there's going to be obvious peptides in there that are not going to be a binder, and actually the vast majority of them. Versus if there's a pre-selection step and only peptides are tested that are pre-selected to be likely to be binders, say because they have the right motifs, it's going to be much harder to make the distinction between what is a binder and non-binder in a set of peptides that all have canonical motifs. So that's why we're doing this re-ranking then of the results to make data sets more comparable. And essentially, we're comparing the methods run within each other and calculating these ranks. This gives us these numbers here, and essentially the higher the better. And the NetMHC pan methods perform the best. The BA for binding predictions, and as we showed on the other thing, the EL, which is actually not so great for binding predictions, perform best for T-cell epitope predictions, as I showed you before. So another big change in the T-cell epitope prediction world has been the massive amounts of data that have become available for a while now, based on MHC ligand dilution data, where peptides are eluded from the surface of the cell and then identified by mass spec, which gives a massive number of results. And they have been used to train methods very successfully. And we also want to use these in benchmark data sets. So the one thing, again, that this goes beyond MHC binding. This incorporates other factors that are important for a peptide to be recognized. One of the things that makes this different from our binding benchmarks also is that presenting a negative data set is not trivial. You're getting essentially from this type of experiment only positive examples. And so we are essentially simulating a negative data set using peptides from UniProt. And that manuscript is now on my desk, should be submitted very soon. This is again then explaining how the method is selected and how we make our recommendations. Then the user can specify alleles and length and their email if they want. That is specifically important if there's a very large data set. It's going to take too long. And if you want the results by email, be notified when it's done so that your browser doesn't just time out. And then these are the results that you're getting where the sequence is echoed. And you essentially have a row per peptide and a predicted score. In this case, this is choosing the MHC EL 4.1 method, where the score is similar to a probability of the peptide to be presented. And here, the higher scores, the better. That is always told here in some, if it's nanomolars as a output value, then you would have the lower is the better. So for MHC class 2 binding predictions, you have a very similar looking interface here. And again, everything is going to be explained in more detail tomorrow. the main things that actually the length criteria here are quite different. And for MHC class 2 binding predictions, we also have a similar benchmarking effort like what I showed for class 1, where we have a weekly, or we're testing weekly if there's new data sets available in the IEDB that we can run across it. One of the issues actually being there has been less MHC binding measurements being done in recent years. And that's also one of the reasons why we want to switch to incorporate the ligand dilution data into these benchmarks going forward. So another important tool, which is quite different from its overall setup, is Epitope, which is kind of like a wizard interface to run the different to run predictions through. And that takes care of that. The predictions are often not just give me this table of peptide sequences, but there's steps involved, like going through multiple protein sequences and doing some kind of only conserved sequences in multiple versions of a protein family or so should be considered. So these kinds of steps are gone through here and guided in a fashion, which is again going to be explained more tomorrow. And then you end up with your overall summary of what you picked in terms of parameters, which can be again run and emailed back to you. And then you get like an overall set of peptides that are intended to be that you can use them directly as they are for your experimental design. Now let's switch to B-cell tools. They are available here on the same kind of interface as I showed for T-cell. And essentially, you have the different types of tools available here, starting with the linear epitope prediction from protein sequences. This interface is essentially a set of prediction methods that are available. In this case, I would strongly recommend going with the Bepi-Pred predictions, which are essentially trained on kind of the features that are associated with being an antibody epitope in linear sequence space. These sequences are then scanned, and this is the kind of output that you're getting, where across the sequence you have essentially a per residue score, and that score is aggregated, in this case, based on a center position of 4. There's like a 7-mer, and 4 is the center, and then that is averaged, and then the peptides that are falling into this are output here as the predicted peptides. Yeah, okay, that's what I said. And you can change those parameters if you would like. Then there's the structure-based predictions, which as their input don't just have a peptide sequence, but have a PDB file that describes the structure. So you can go in here if you have a PDB ID, just put this in directly. You can also upload a file. So if you're using a structural modeling program such as AlphaFold, you can enter the sequence, get your PDB file out, and use that here, and then essentially start the program, which then gives you actually a similar output first on a per residue basis, and then this is repeated here when you click on table view, you get that in a table format, which you can use directly, or you can click on 3D view, and then this viewer opens in which you can actually look at where are these residues located on the surface of the on the structure, and that is obviously the difference with the linear epitope prediction method, which takes no account into what the context is in which it is may or may not be accessible to an antibody, versus in the 3D structure you might see that regions from different parts of the linear sequence come together in the 3D fold and form a region that might be very, very good at being recognized by antibodies. So now let me switch away from the specific tools and go to something the kind of ways you can access these tools. So one version is if you have a download available, where you can run programs on your local machine. The big advantage is that there's no internet needed, and if you have large data sets, this is going to be much more efficient than running it on this browser. This is free for not-for-profit in academia. If you are working in commercial industry, we ask you to, which actually was one of the driving forces that made us implement these downloads, because they were not allowed typically to use their proprietary sequences that we were working on a public server. So they were asking us to provide like standalone, so that's why this came about, and everybody else benefits from it, and it's being supported by these license fees that industry pays. So then you can essentially run the same kind of, this should output look familiar. This looks pretty much exactly like the output that is shown on the web page, but you can run this now on the command line on your computer. And then here, this is just an example of how the predictions will look like. Then there's the API version where essentially predictions are again run at the servers at LJI, but you can call these like any other API in a RESTful fashion, meaning you can just there's no state transfer, meaning you can just run things over and over, and it doesn't there's no state saved from the server. This is again freely available to all users, and you can the main advantage is you can include this in some kind of prediction pipeline, so you don't have to pop up a browser and run something. And so here's an example how this can be run for T-cell epitope predictions, and where again you have some kind of input like this, where you have your peptide and your allele, and then this is a script as an example how this can be called, and then you're getting your output back, and you can imagine that you can integrate this into some broader pipeline or so that you're working on, which will allow you to run anything start to finish without having to do something on the server. So this is the 3 types of access points I mentioned. The web stuff is that I just went in first. That is obviously always we recommend starting with that. That's the easiest, and if it's at least to try stuff out, it should always be nicer than having to go through downloading a standalone, etc. This is again like easy to run for very large data sets. This is still going to be problematic, and the other advantage is actually it's automatically updated. So whenever, like I showed you with the recommendations changing, we will have the newest version running there directly, versus if you download the standalone, if there's an update, you will have to install a new version of this program. And obviously there's some minimal computational expertise needed to run it. It's great for large data sets. And again, there might be a license fee involved. And then the API runs on the command line interface and can, sorry, uses command line interface. Sorry, I should have said that. But you can be called from a script and incorporate into any other tool, and has the advantage, like the website, that it's going to be automatic. So let me summarize this here. So one thing, I actually should have said this at the very front. So all these tools, specifically the prediction tools, are meant to give you candidate epitopes. If something is predicted to be a good scoring peptide, that gives you confidence that this is going to be more likely to be an epitope than a low scoring one. But this is no proof. You will have to ultimately experimentally test it. And the easiest way to do that is actually check, has this been tested by someone else before? That data should be in the IEDB. So first, if you're interested in epitopes, check what's already been experimentally tested. And then otherwise, you can use these prediction tools, to do in silico studies or predict candidate epitopes for further testing. We're using machine learning to identify these things by extrapolating from what we know. We're using our C-curves to evaluate prediction performances. Again, this is a screening step, not confirmatory, and should be experimentally tested. And then the analysis tools that are going to be talked about later are more about taking sets of known epitopes or predicted epitopes or so, and then do something with that set, like running the clustering analysis or so. So that's it. Again, there's the classic and the next generation site. And if anything, there's lots more coming up on those, specifically tomorrow. And if you like this and you want to know more, or if this was too easy and too trivial, definitely come back and maybe test them out in between. Definitely, if you haven't tested the next gen tools out, this would be a good opportunity to do that, and then ask some questions tomorrow. And with that, I am done.
Awesome. Thank you so much, Bjoern, for giving that talk. And as Bjoern mentioned, you'll hear much more about the tools tomorrow. And now we'll be moving into our first Q&A section for the day. So I'll invite Alex back with Bjoern and give Bjoern a chance to have a quick look. If it's okay, Alex, I might just take the first question because we received a few comments about the slides. Normally we share this kind of at the culmination of the workshop, but I've managed to save all of the finals in our drive that we have. That drive that I usually share around the break, but it is in the chat at the moment. So it's got papers, different one-page summaries, things that you might find useful if you'd like to browse. But also there is a subfolder with the day one final presentations. So check that out if you are interested in following along in real time. And then also some questions, as we answer them, they move into the answered column. We'll pop some notes in there as well. So feel free to look at that and I'll repost the link there. But Alex, I will hand it over to you.
Okay. What were the questions? There was one question regarding whether at this point we can just use prediction tools and get away from testing things experimentally. And I think Bjoern addressed that in the sense that no, if the prediction tools are a very useful guideline and do a terrific job in narrowing the field, but specifically, MHC binding is a condition that is necessary but not sufficient for immunogenicity. And the something that binds may or may not be recognized on an epitope depending on a variety of different other things, including processing, including, for example, whether there is peripheral or central tolerance against that peptide, whether there is conversely pre-existing immunity and there are clones that have already been expanded. So it's unfortunately, I think there's still a big role for experimental validation of the lead identified by the prediction. Bjoern, you had one, but you
I can
were
take,
going
I'll
to
take the next
answer.
question. Okay, the next question I have is from an anonymous attendee. It says, in the epitope tab, the HLA allele is not given. Why? How can one retrieve it, even if there were multiple associated with? So essentially, the epitope tab really just gives the structure of the epitope itself. And as the user already points out, the restriction of the given epitope can be very different in different contexts. So you might have an epitope tested, say, in HLA transgenic mice, and that says it's HLA A0201, and that might be the only evidence for it. You might not want to have that. So essentially, the experiment itself defines restriction. So you have to filter by that epitope, and then in the assay tab, you'll see for each of the assays that were performed with this epitope, what the restriction was. So there's a column there, MHC restriction. Or you click on the epitope ID itself, and then you're getting this summary view of all the data with the epitope that has the different restriction information at the bottom. So, and I guess one of the things that we've been struggling with for some of the things that have been tested for a long time, you're going to have like 40 different MHC alleles, but really some of them are just spurious, and others are like the famous HLA A0201 epitopes that Alex was pointing out. There might be 100 different experiments from different people that have shown this, and we do want to work on a summary for that. But right now, you're getting a table that essentially gives the evidence for the different restrictions, and you're going to have to be saying what of that you believe. I hope that answered the question. Alex.
Yes, so there was another question from Bedaso Dao. Does the database contain epitopes for animal pathogens? And the answer is yes. Short answer. Longer answer is animal pathogens depends whether you are. So we curate things from all animals and species. So we curate different sources. So an epitope that is recognized in humans or mice or non-human primates. It can also be that an animal is source of a pathogen, and for example, is very a very good example is perhaps people can be allergic to cockroaches or to mice droppings and so forth. And so we certainly curate, for example, allergens from different animals. Another example is, for example, people may be allergic to milk from cows. And then we curate those. So the answer is yes. Bjoern, you want to take the next one?
Yep, sure. The next one I have here is from Kieran, who asked, how can I download antigen data from IEDB in faster format for in-house analysis, such as using BLASTP to access the antigenicity of new epitopes in cancer vaccine research? So we do not have an ability to download sequence data in fast format. What we have is that when you download your results tables, there is a column with a UniProt identifier of the antigen. So you can take that, go to UniProt, get the sequence out. So that is essentially, we don't provide the faster sequence, but that is the way we have it. And maybe because we have a few, Alex, I'll just take the next one. Anonymous user asks, are you using or will you use artificial intelligence to search for data? The answer is you can use ChatGPT now, and they actually have gobbled up the IEDB and can ask questions, and so they're good with that. And we are thinking about having query interfaces that take advantage of that. At the same time, we really want to focus our current, we still want to be, I think the advantage obviously is what we have is a very exact interface without hallucinations. And you can ask, so the ability to query exact and giving exact evidence for everything that we present should have priority. It can be useful to use AI for search to especially make like first initial queries. Yeah, I'm done here, Alex.
So Kiran is asking, are predictive models for HLA binding affinity trained on all HLA class 1 and 2 alleles, or are there limitations for rare alleles? If not all alleles are included, how might this affect the model accuracy for predictive binding affinity for rare alleles? So Bjoern can help keep me honest, but yes, all the data is utilized to train. Certainly it is true that rare alleles may have more scarce data available for training, which may affect the reliability. On the other hand, also there are other approaches where often rare alleles are very minor variations on the binding specificity of much more frequent and more well-studied alleles. And in those cases, in fact, there are predictive algorithms that use the overall pocket composition to predict binding affinity. Bjoern, would you like to add anything on that?
Nope. You're all good. And I'll take the next two that I marked here, Alex. Next one is from an anonymous attendee. As for the prediction model Bjoern explained, is there any data on the antibody side as well, or all data provided on the antigen side? Thank you. So we have multiple methods available right now under development and in final stages of development that will be antibody specific or utilizing the antibody sequence in itself. So I should actually, the simplest one is actually kind of the sibling tool to TCR match. We're essentially saying, okay, if you tell me the antibody sequence, is another antibody known that has similar sequence composition and therefore is likely to predict to bind the same epitope. So that's what we are working on. We have other approaches in the works that are more advanced. So yes, this is definitely an ever increasing field of interest. It had been all of these really rely on large sets of antibody data with known affinity or TCRs with known epitopes, and those data sets are still relatively scarce, or in many cases actually quite overlapping. But yeah, this is definitely coming up. Then the next one here is, can you elaborate more about the negative data set for training? How was it done before versus the one you're planning to publish? I did not talk about negative data sets for training. I mean, those were always, that's every method does that by itself, decides how to do this. this is about MHC ligand elution data, I assume. I was talking about testing, where we essentially then embed the set of sequences that we have of positives in MHC ligand elution data into kind of like a universal background of what are general peptides, so which are essentially then posited for negative peptides. So essentially, you're trying to identify positives from an unlabeled population, and that's kind of how we're doing it. And we've compared different ones. I ask you to wait until that paper comes out. Thank you, Alex.
Kiran asks, how reliable are predictive models in estimating antigen properties for disease-specific studies, such as cancer, when the model is trained on a diverse data set that includes various diseases? Would a model trained on such broad data accurately predict properties specific to cancer antigens? That's a great question, and it's a valid question. And in fact, we're very excited that recently we have been able to establish this sibling database, a CEDAR database that relates with cancer specific, because it's quite possible. And in fact, in the case of cancer, there is the whole underlying dynamic of the fact that maybe the epitope is a self-epitope, in which case you would have other features of tolerance, but mostly also the epitope may be a neo-epitope or a mutation, where there are different rules that may influence that. So we look forward in the scenario we're actively working on. And the short answer is that many of the predictive tools have been trained either on infectious disease data, because that was not broadly available, or on eluded data, which then you could argue, but it's a different dimension. And I don't know if Bjoern wants to add something on that.
No, that was perfect. The next question I have here is,
so then there's another question that I can quickly answer. What criteria, an anonymous attendee is asked, what criteria of selecting HLA from the set? So I'm not sure I totally understand the question, but I'll answer the question that I think is related to that. And certainly there are thousands of different HLA alleles, as has already been alluded. And so the question is, how do you select which HLA to make predictions for? And of course, there are two answers to that. One, if you know what is the HLA of interest. So for example, if you have a cancer patient and you know what is the HLA type of that cancer patient, you can select those matching alleles. Or it could be that you have a trial that is focused on epitopes recognized in a population in Nicaragua. And if you know what are the alleles that are expressed more frequently in the Nicaragua population, you can run prediction for those. In general, we have worked to select reference set of alleles that are the ones that are most frequently expressed in worldwide population. And those are usually a set of 27, 25 to 30. And you can actually select specific alleles, this set of reference frequent alleles. When you run prediction, there is an option to select those for most frequent worldwide alleles. Bjoern?
So Bjorn's muted, I think. Sorry, Bjoern. And we are at 9:20. Do you want to take another couple of questions?
I'm just going to do the next one. Okay, just because I have it. Oh, here it is. Okay, from Sharmona in MHC1 binding prediction, in MHC1 predictions, what does the percentile score indicate? So the percent, it's kind of like similar to what I just talked about in terms of the negative data set. You're taking a large set of random peptide sequences, and random here is actually an interesting question, but and then rank where does your peptide fall within all of these random peptides if you predict them for binding. And so whenever we have these percentile score, it's kind of like a renormalization of the kinds of outputs of the binding affinity or other probability scores, so outputs that you have. And one of the big advantages, and that's actually relating to another question we have down there, is that this allows to kind of merge and compare outputs from different prediction methods that are on completely different scales, because it kind of normalizes the kind of output that you have based on this large set of 100,000 or so random peptides that are run through each of the predictions. And with that, I'm done. And I think, I mean, we could say, like, lots of these, we have more Q&A sessions later, definitely for the tools, the whole day tomorrow. I would probably not do those now. Nina, if we want to keep on time. I don't know if Alex has the last one or if he's also done.
I think I'm done. I'm answering one, just typing, but we don't need to.
Awesome.
I can answer. An anonymous attendee said, considering the difficulty of performing your own binding assays, do you have a recommendation for outsourcing to a professional assay providers? Well, my lab on occasion has run binding assays, a collaboration or outsourcing, but we don't do that very much. I think that there are some CROs that provide that as a service, but I can't really tell you off the top of my head. I think you can probably Google it and look for binding assays. Some of the people that do immunogenicity services might be able to do that.
Awesome. Thank you so much, Alex. Thank you, Bjoern, for that super strong first Q&A. So thank you all for your questions. As Bjoern mentioned, we still have some unanswered ones. We'll try and type some answers, or we'll cover most of them tomorrow, because tools is tomorrow.